Hey, hello and welcome to week 4 of problem solving session for the NPTEL course on Principles and Applications of Building Science. This course is being taught by Dr. Ilangovan Rajshekhar, Associate Professor at the Department of Architecture and Planning, Indian Institute of Technology, Roorkee, IT Roorkee. I am Isha, PMRF and Research Scholar at the Department of Architecture and Planning, IIT Roorkee. So a few housekeeping rules for the session. Please mute yourself for the session. If you have any questions or if you want to discuss the answers, you can put them in the chat box. If you have any queries at different points during the video, I will ask you to raise your hand and unmute yourself for asking questions. So please do that at that point of time. Okay, so moving on, the outline of the session is such that we're going to look at the highlights from each of the week, which is we're going to look up at the key takeaways from each of the lecture units in week 4 content. Then we will also look up at assignment questions, especially relating to week 3 assignment questions with their explanations, because the deadline for week 3 assignment has passed and you would already have submitted the answers. So if any queries are there regarding week 3 assignments and how they have been solved, you can refer to this particular section. And then we'll also look up at solution to week for assignment questions from the previous run of the course. That is from the last run of the course, we will look up at the assignment questions. So none of these assignment questions are repeated and are presently in week 4, but you will get an understanding of how to solve more questions for practice based on week 4 content. And lastly, if we received any queries from you, we would also clarify these queries based on queries if any queries were received in the discussion forum relating to week 4 content. So week 4 looked up at the visual quality in built environment, the effective daylighting design and an integrated design approach. So we will now look up at highlights from week 4. So week 4, the first lecture was lecture 16, which looked up at acoustic quality indicators. So this is part 2 of the acoustic quality indicators. Lecture 15 from week 3 also looked up at a few acoustic quality indicators. So we ended lecture 15 on these 4 measures for audibility of information. So these are articulation index or AI, not to be confused with artificial intelligence, but uh, especially in sound studies, the subscript AI is referred to as articulation index. Then the second measure is the speech intelligibility index or SII. The third measure is speech transmission index or STI, and the fourth one is clarity. So we will now look up at all of these terms. So articulation index is primarily used for understanding for the intelligibility and privacy measurement in office spaces. So this is an index which is used, which is basically defined as a ratio between the voice level and the steady background noise. So for minimal distraction, the articulation index or an AI value is between 0.35 or less. So anything from 0 to 0.35 is minimum distraction. That is, your voice level is much more clearer and you don't have much background noise. Then for normal speech privacy, that is in which an average person can work without any distraction, although there are occasional parts or outside conversations which are happening or which can be heard. So that sort of sound environment corresponds to an articulation index of 0.2 or less. So this is normal speech privacy, where you still hear outside noises like the moving of a fan or outside vehicle or traffic noises, but they do not affect much or do not distract you from your work. Then we have the confidential privacy, which is when the average person can carry on discussions with assurance that he or she will not be understood by neighbors, corresponds to an articulation index of 0.05 or less. So this is when you are speaking very closely to a person, like on a one-on-one conversation, and the person who's standing at some distance could not understand what you are speaking or what the two of you are discussing. So that is confidential privacy with an AI of 0.05 or less. And when the articulation index exceeds 0.4, then there is no privacy. Okay, so this is articulation index, the ratio between the voice level and the steady background noise. Okay, and they are determined in terms of what the average person can hear or do in particularly, especially in office spaces. Okay. Now the second index is measure is speech intelligibility index or SII. So this is more complex to calculate than the articulation index, and it includes device frequency weighing and the masking effect of one frequency band over the, other or nearby frequency bands. So for the same condition, SII values are slightly larger than articulation index or AI values. So zero SII corresponds to completely unintelligible sound environment, whereas one is for a perfectly intelligible sound environment. Okay. Then the third measure is speech transmission index or STI. So this is the speech intelligibility within performance and lecture spaces. So unlike articulation index and our SII, the speech transmission index, it takes into consideration the room reverberation into account as well in its calculations. So room reverberation is when the certain sounds reflect back from the different surfaces. So while the STI can be measured directly from instruments, the articulation index and the uh, speech intelligibility index or SII cannot be measured directly from instruments because they are based on the articulation index is based on the average person's hearing capacity and things like that, and how they perceive how much background noise they can perceive as normal. So articulation index depends on this, and SII also depends on the frequency bands and things. So you cannot directly measure them with instruments, but speech transmission index or STI you can measure directly with instruments. So it measures the band level between 125 and 8,000 hertz. So between 0 to 0.3, if the STI is between 0 to 0.3, then it is a bad sound environment. Then if it's between 0 to 0.45, it's a poor sound environment. And these are especially particularly used in lecture spaces and things. And then between 0.45 to 0.6, it's fair. 0.6 to 0.75, it's good. And above 0.75 to 1, it's excellent. So all of these are indexes between 0 to 1. Now we will look up at, then we also have a RASTI, which is Rapid Speech Transmission Index. And this is especially used for human lecturers, like speaking in small rooms without any echoes. So there are certain calculations and formulas related to it. So these are for small rooms without any echo effect happening. Then the fourth measure is the clarity of sound. So the clarity index C80 measures the total sound energy arriving before an 80 millisecond threshold. So this is basically the total sound energy arriving before any before the sound threshold, and that threshold is established at 80 millisecond threshold compared to the total sound energy arriving after that threshold. So whatever is coming before that threshold to the ratio whatever sound energy is coming after that threshold. And this is averaged for the four mid-frequency octave bands, which are between 500 to 4,000 hertz. So C50, which considers a sound threshold of 50 millisecond, 50 millisecond is meant for speech, and then C80, which considers the 80 millisecond threshold, is meant for music. Okay. So these are the four indexes basically. So C50 describes the intelligibility of speech and also of singing, like how clear how clear are words in the song, or how clear are words when a person is speaking to you. So you can then calculate these based on these different formulas, which is the sound energy which is coming on 50th second and before 50th second to after 50th second. And similarly, CAT is used for temporal transparencies of musical performance when there are instruments and other things. So these are a few measures which are used for measuring the acoustic quality. Then we also have room mode. So room modes is the phenomena which occurs when sound travels between two reflecting surfaces. So in a room, these reflecting surfaces are basically your walls or your roof and other things. So anything which because sound moves in a waveform, as we looked up at in week 3. So these waves, when they encounter an obstacle, they sort of reflect back. So that is why the movement of sound in the room leads to these room modes, which is this phenomena which occurs whenever sound travels between two reflecting surfaces, where the distance between the surfaces is such that the impinging wave reflects back on itself, creating a standing wave. And these are especially low frequency ranges in small rooms is considered. So there are basically three modes of transmission or reflection of these waves. So you have the axial mode, the tangential, and the oblique mode. So the tangential mode is when it reflects in a particular horizontal plane. And the oblique mode is when it goes beyond that plane, which is what is usually happening in in a typical room. It does not follow a plane. And then natural is when it considers all of this. So you can measure, calculate the frequency of the wave, the standing wave which is being generated. So it is based on the formula which considers the speed of sound, the length of the room, the width of the room, and the height of the room. And then there are these PQR, which are integers between 0 to 4 and so on. So you can basically calculate the frequency of the new wave which is being generated in these cases. Okay, now moving on to lecture 17, where we also looked up at the acoustic design considerations, where we looked up at general design considerations for design of spaces where sound is a key parameter, is of key importance, like your theaters, which have a major sound component, your orchestra halls, lecture halls, uh, anywhere where there's a speech environment, where speech is the most important form of communication or is what you're listening to. So these considerations includes like the reflection of sound, that is how directly sound is traveling and how the reflected sound comes to that person. There should not be much delay. So this is what the figure also shows, that a person standing on the stage, this person standing on the stage, when this person speaks, he has the direct sound component as D, whereas because of the waves which are being generated, there's also a reflected component which is coming to him through A, B, and C. So A, B, and C minus D, if it is less than 60 feet or 18 meters, there's going to be an early sound reflection that will support the loudness and speech articulation and musical clarity. But if this distance is greater than 225 feet or 68 meters, there's going to be a late sound reflection, which if it is sufficiently weak, it will not be heard. Will be heard as part of the reverberant tail of the impulse response. And if it is sufficiently loud, it will be heard as an echo, because this person has already heard whatever the speaker has said, and the traveling of the sound wave took some time. So this person is hearing the same thing again. So he will associate it with it as an echo. So in designs, we try to achieve this A, B, C minus D is less than 18 meters, especially in your cinemas, theaters, lecture halls, and all of these things, such that this eco effect is not being considered or does not ruin the quality of the performances. Okay, that is one aspect. Then again, we have similar different things. So these are particularly for special sound environments and things. So usually you have a steeply rigged seating to allow clear line of sight and promote access to direct sound. So each of the person who's sitting on these lows can directly see, and is not his line of sight is not being blocked by the person sitting in front of him, and also such that these person have access to direct sound which is coming to them, and do not this path is not being broken basically. So this is the first thing, like this steep drake setting is both for visual comfort as well as acoustic comfort. Then we also have this suspended canopy to direct the early arriving first order reflections to the listener, because this person is speaking. So some of these sound waves are going to travel up, and because if this was not there, it will go up and it will take a longer time to come. So A, B, C, D, again, the same thing. So ABC minus D should be less than 18. So you can put like a suspended canopy which will reflect these early sounds such that they go directly to the listener and arriving as first order reflections to the listener. Then if you have a balcony, or if you have, because you have limited amount of seating which you can put because of the slope which you are maintaining. So you could also have balconies on both sides of the sound environment, or this particular room which is shaped for speech or cinema, such type of performances. So balcony to bring listeners closer to the audience. Then you can have similarly this type of profile is beneficial for early arriving first order reflections which are coming again from the speaker, and such that they bolster the loudness and intelligibility index in the rear of the room, and it does not is not causing echo effects to these listeners who are sitting on the uh, like sitting behind in the spaces. Then you can also use sound absorbing materials, which can be applied on the total area size to optimize the reverberation time. We will look up at what is reverberation time and how to calculate it. And you also place them on the back of the upper rear portions of the side walls, such that the sound is absorbed and do not travel beyond these spaces. So then again, you basically use geometry and sound reflection properties such that each of the listeners have access to direct sound as well as the reverberation or the reflected sound does not cause an echo effect. Also, you also need to ensure that there are no dead zones where sound is not reaching only, or where the articulation index or SII or STI are much lesser. So you need to ensure all of those calculations again. Then you also have effects like echo, where you hear the sound after a long period of time. Then you have flutter echo, where you keep hearing the echo happening. Then there's focusing, where the particular person uh, is being is hearing the same sound again and again. And similarly, creep is also one of these acoustic defects which happen in these spaces, and they can happen from both concave as well as convex surfaces as well. So then we have indices which are used for measurement. So we moved on to lecture 18, where we are looking up at acoustic materials. So we are looking up at indices for measurement. So first, we are looking up at sound absorption of a material. So we are here looking up at the reverberation time, or TR, which is given by the formula 0.163 V by A, where V is the volume of the room or space, and A is the absorptance into area sum for all the different surfaces which are present inside that room. So the absorptance of east wall into the surface area of east wall, plus absorptance of west wall into surface area of west wall, plus absorptance of north wall into surface area of north wall, plus absorptance of south wall into surface area of south wall, plus similarly for roof as well as for floors, and if there are other surfaces like that. So A is the sum of absorptance into surface area of all the different surfaces on which sound is striking, basically, and V is the volume. So you calculate the reverberation time using this equation. And then this can also be measured using two different methods. So you have the reverberant chamber method, which is limited to 100 to 5000 hertz frequencies. And you have the impedance tube method, which is also known as the standing wave method. So more details on this can be found in the lecture 18. So if you want more details, you can look up at this particular unit. But reverberation time is fairly simple to calculate if you know the volume, the surface area, and absorptance of the different surfaces. And we will look up at numericals also to solve these questions relating to if numerical questions come. Then we also look up at the NRC, or the noise reduction coefficient. So this is an average of how absorptive a material is at four frequencies, which are 250 hertz, 500 hertz, 1000 hertz, and 2000 hertz. So NRC is measured for the four different frequencies, 250, 500, 1000, and 2000. And this measures how absorptive your material is of sound waves, basically. So if a manufacturer, so for example, a manufacturer of a wall carpet product can provide an NRC rating of 0.8, which is extremely good, okay? But if there is fine print, be sure to read if you may see that this rating was achieved while the carpet was installed over the fiberglass. So fiberglass by itself is a very good sound absorber. So in this installation configuration, the fiberglass, not the carpet, act as the sound absorber. So within the acoustic material behind the wall carpet will provide only, will probably only achieve an NRC of 0.2. So for example, if this wall carpet manufacturer tells you that the NRC, or the noise reduction coefficient of the carpet or the product, is 0.8, but it is actually being measured, or when this NRC was calculated, it was calculated over the fiberglass board. So the carpet was placed on the fiberglass board, and then the NRC was calculated. But the fiberglass itself is a very good sound absorber, so it will also absorb the sound which is coming. So the carpet and the fiberglass together have an NRC of 0.8, and not just the carpet. So if the testing method has this discrepancy, a manufacturer will not say this to you, but you have to be aware of that the particular material on which this was tested will also have its own NRC value. So the wall carpet probably by itself only had an NRC value of 0.2, but the manufacturer, because he was trying to boost up his sales, will tell you that the NRC was 0.8, and you would assume that it's a very good NRC and you would buy the product. But in actuality, the NRC of the wall carpet is 0.2 only, which is fairly poor. So you would buy a product which is not very essential or very useful for you, because you would place it on a stone floor or a different type of floor, and will not give you the same NRC value. So these are things you should understand, how these measurements are done and what is the fine print to be read. Okay, so this is just an example of NRC. Then we also look up at three different type of acoustic absorbers. So we have the porous absorbers, which are like a foam sort of thing. So they absorb sound in the white spaces. Then you have panel absorbers where there are panels. Then you have cavity resonators where there's a cavity behind these boards, which is used for holding the sound in. Okay. So then when we look up at porous absorbers, they are more efficient at high or rather low frequency sounds. And their efficiency improves in the low frequency band with increased thickness and with the distance to their solid backing. And they're usually perforated or fissured or textured materials. And they are available as acoustic boards, hangers, geoacoustic tiles, which you can directly place in your rooms or where you want more soundproofing. And other variants includes including them in plasters or sprayed fibrous materials, putting them as blankets, foam boards, carpets, and fabrics. So they also enhance your sound environment in your particular room. So these are porous absorbers. Then you have panel absorbers, which are basically impervious materials, which are installed in a solid backing, but they're separated from it by an airspace. So, for example, you have a board, then you have the wall basically, and then you have the box frame. Then your installation is glued to the back of the panel, and then this is your basically your panel absorber. Okay, so it absorbs the sound directly, and there's a this wall cavity which is being maintained from the wall or this wall structure basically. Then the third type of acoustic materials are cavity resonators. So these are also known as Helmholtz resonators, and they consist of an enclosed body of air, which is confined with it rigid walls and connected by narrow openings to the surrounding spaces. So you have these narrow openings basically, which is opening up. So each of this hole is like this basically, and it captures the sound and stores it in. Okay. So there are calculations for the frequency of the wave which is entering this. And again, it is dependent on the velocity, the cross section of the neck, or that small space which we saw. Then the length of the neck, the radius of the neck, and the volume of cavity. So neck is basically this. So what are we referring to as neck? So these cavity resonators can again be of three types. You have the individual cavity resonator, where there's only one cavity basically. Then you have perforated panel absorbers, which are like multiple holes but a single cavity behind it. Then you have slit resonators, which are like longer slits formed. These are like the perforated panel absorbers. Okay. Then we also have something known as the STC rating, or the sound transmission rating. So a single number rating of a material or an assembly's ability to resist airborne sound transfers at the frequencies 125 to 4000 hertz. So these are basically seen in the type of insulation like rigid panels, spray, polyurethane foam, SPF, the structural insulated panels or SIPs, blankets, bat insulation. So these are the STC ratings. And if we look up at the STC rating, so if you see 20 to 25 is poor, and its use, it basically translates into low speech audible. Then 25 to 30 is poor, where normal speech is understood easily and distinctly. 30 to 35 is fair, where loud speech is understood fairly well. 35 to 40 is good, where loud speech is heard but is hardly intelligible. 40 to 50 is very good, but it is not understood, where loud speech is heard faintly. So the best or the excellent performance is for the sound transmission coefficient of 50 to 60. So this is loud sound heard faintly or not at all. Okay, so you want, so this is basically resisting the airborne sound transfer at these higher frequencies. like within the hearing frequencies. So if you want to ensure that the STC is of a higher value of 50 to 60, so that loud sounds are only heard faintly and not at all to the outside spaces. So this is the sound transmission class. Okay, then we moved on to lecture 19, which looked up at lighting. So 19 and 20 are both based on lighting and an integrated approach. So now we will look up at lighting basics. So light is within this visible light basically is within this uh, band wave of 400 nanometer to 700 nanometer, and light is basically the visible portion of the electromagnetic spectrum which we can see. Then you have the ultraviolet and the infrared radiations on the other side as well, and then the other radiations as well. But light is what we consider for in building science studies. So a few key terms like light power, which is the amount of light emitted from a source. So equivalent of this is the water flowing in a pipe, and the diameter of the pipe determines how much water flows. So similarly, light power is also the amount of light, the light which is emitted from a source. And this is expressed in the unit called lumens. Lumens is the SI unit for light power. Okay, so this is the analogy basically. Then we have luminous flux, which is also expressed in lumens, LM, SI unit is LM. Or lumens. The luminous flux is the rate at which the light energy flows from a source. And 1 lumen is the flow of light which is emitted by a unit intensity. The intensity of light is measured in candela. So 1 candela, CT, is the by unit intensity 1 candela point source within a unit solid angle. So the surface of the sphere subtends like 4 pi radius, 4 pi unit of solid angle at its center. So 1 candela point source will emit 4 pi lumens in all direction, which is 12.56 in this case. Like 4 into pi is 12.56 basically. So it will, 1 candela point basically emits 12.56 lumens in all the directions. Okay. Then, so the intensity of light, as we mentioned previously, measured in candela or CD, a PSI unit. So it is the quotient of the luminous flux on the element of the surface, normal to the direction of view, divided by the solid angle in steradians, subtended by the element at the source. So intensity is measured, defined as the luminous flux divided by the solid angle. So I is F by omega. So F is luminous flux and omega is the solid angle. You can, if you want further details on this, you can refer to this particular lecture. I'm just covering the basics and revising the concepts, so I will not go much in detail into all of these things. So this is the definition and the units and things relating to intensity of light. Then we have another thing which is illuminance. So we looked up at illuminance also in the um we looked up at the solar illuminance or solar irradiation and things. So illuminance is basically the amount of light which is falling over the surface. So we have solar illuminance, which is the amount of sunlight which is coming inside in the inside spaces. So luminance is basically the amount of light which is falling over the surface, and this is expressed as lux or foot candela. And then the brightness or luminance is the amount of light perceived or measured to reflect off a surface. So the brightness of light. And it's also a function of the eye's adaptation to the contrast which is being observed. Luminance is also an objective measurement of the reflected or emitted light per surface area. And this is measured as in like candela per meter square. Then there's also glare, which is the effect of brightness or brightness differences within the visual field, which causes annoyance, discomfort, or loss of visual performance. Then you have two types of glare categories. Basically, you have the discomfort glare and you have the disability glare. So discomfort glare is when you are you experience discomfort because of these very high brightness which is falling in your visual field. So that is discomfort glare. So when you are sitting on, you have the window behind your back and you're working on your computer, and suddenly a very strong, during the morning peak times, there's a strong sunlight coming through that window. So it's affecting your ability to work. basically. So that is disability glare, that is you're unable to work or carry out your functions because of your because of the effect of glare, or this brightness level which is coming in, because it is getting reflected off your laptop also. So that is an example of disability glare, where you are unable to perform the daily activities or tasks because of this glare effect. Okay. Then we have indices for measurement. So we have these light input parameters which influence the quality of our work or our productivity. So we have illuminance, which is the amount of light which is coming on a particular surface. Then you have luminance, glare, the negative effects of glare, the spectral energy distribution, color temperature, color rendering, flicker. So if a light keeps doing going on off like very frequently, you feel that is the flicker effect of light. Flickers also if you have, for example, a light over a fan. So because of the movement of the fan blades, the light keeps getting cut at particular intervals. So you that is also an example of flicker which will affect your productivity. It will give you headaches and you will not be able to work properly. So these are parameters which needs to be considered in design of spaces. So yeah, also daylight is an important component in building design. So you would want to have the maximum amount of daylight coming in, such that you do not have to rely on artificial lighting during the daytime, especially. Most of the offices buildings are designed such that they use uh, artificial lighting instead of daylighting because of effects of glares and other things, because most of the office buildings have like glass facades, so a lot of glare and other things, direct sunlight components are much stronger. So they then use some sort of shading or shutters to block out the sunlight, and then they rely on artificial lighting, which is not something good buildings tend to do. So you need to ensure in your buildings that daylight is the major component through which the building lighting requirements are being met, especially during the daytime hours. And this is also in terms of improving the light quality, then improving uh, reducing the auxiliary light use or the artificial lighting use. So both reduction, the cooling load reduction, energy saving. So all of these are basically connected to each other. Similarly, improved light quality is also associated with increased productivity and sales, better occupant comfort and health, which leads to your labor cost saving and things. So all of these effects are directly uh, cumulative, basically. So daylight is an important component, especially if you're designing buildings. Then another term is the design sky illuminance. So this is this is basically the value, the location receives design sky illuminance 80% of the time between 9 a.m. and 5 p.m. So this, that the value of illuminance, assuming like a horizontal surface, that is the design sky illuminance. So it's basically dependent on the location. Then we have the daylight factor, which is the illumination indoors with to the ratio of the illumination outdoors. So you want a daylight factor to be higher. That is most of the illumination in the indoor spaces are being met by the outdoor needs, basically. So there are different benchmark and standards which say this is the design factor you should achieve in this type of buildings and things like that. And this is also an indicator of the effectiveness of a building design when bringing daylight in directly to your buildings. Then you have the direct component of sunlight, and you have externally reflected components because of certain obstacles in the path of light, basically. And then you also have internally reflected components, which are based on the reflection from the inside of these spaces. Then you have different measures for measuring the daylight at different things. So there are basically three type of lighting requirements which you need to ensure. One is for task lighting, which is, for example, if you're studying, then you need to ensure that your study table is at a certain lighting level. Then you also have then you also have the ambient that type of light as well. So for the estimation and measurement, we use nomograms and lux grid method. And these are used for the different types of spaces. For example, this table gives you the daylight factor expressed in percentage as the for the different spaces. So for art studios and galleries, you can have a daylight factor of 4 to 6. For factories, laboratories, 3 to 5. For offices, classrooms, gymnasiums, kitchen, a daylight factor of 2 is good enough. For lobbies, lounges, living room, churches, you don't need a much higher task lighting. So you have a daylight factor of 1. For corridors, bedrooms, it's 0.5. Then, in terms of for glazing systems, we looked up at solar heat gain coefficient in the previous lectures. Now we look up at the visible light transmittance, which is also one of the important factors in windows and fenestrations design. So VLT is the factor which quantifies the visible light that passes through your glazing or through your window glass, and this is the light to your solar gain ratio. So visible light transmittance is also affected by SHGC. Now moving on to lecture 20, where we look up at the lighting design concepts and how to include daylighting into your building design. So you need to ensure the effective, efficient, and realistic usage of daylight in terms of methods of harnessing it and harvesting daylight into your building and bringing it inside. So there are basically 3 measures through which you can do that. One is effective fenestration design, where you give due consideration to the solar heat gain coefficient, visible light transmittance of the glass, the U value of glass, U value of frames, and all of those things. So you ensure effective fenestration design. So VLT is the component which is directly responsible for your light, the amount of light coming inside. Then you make use of daylight harnessing systems like light pipes, light shells, and all of those type of things, which we will discuss also. And then you make use of daylight harvesting device and system in terms of controlling them and how to make use of opening and closing controls and those sort of things. So these are 3 measures to which you can harness daylight. So one is daylight systems with shading. So shading is also an important component, and we have discussed shading in previous lectures, particularly week 2. So these are systems that rely primarily on the diffuse skylight and reject direct sunlight. So you basically prevent the harsh, because sunlight is also associated with this component of heat gain. So you want the diffuse skylight to light up your inside spaces or be the lighting component for your building, but you don't want the direct component or the direct sunlight, which also has this high solar irradiation values or the heat gain factor to come inside your buildings. So systems that use primarily direct daylight, sending it onto the ceiling or to locations above the eye height. So those type of systems can be used where you want to have daylight systems, but you don't want to. That is, you want to use the diffuse skylight, but don't want the direct sunlight. Okay, so these then the second is daylight systems without shading. So you can have diffuse light guiding systems, you can have direct light guiding systems, light scattering or diffusing systems, which are used in like top lit apertures, which cause glare if used in windows, and the light transport systems. So, for example, your light shelf is a type of uh, daylighting control with shading. So what it does is basically you have a shading and you allow the in the winters because the sun angle is low, the winter direct and diffuse sunlight can come in directly. But in summers, when the angle of the sun is much higher, the direct component of the light gets hits this light shell basically, and it gets reflected from the ceilings and then goes into the inside spaces. Then you can have different tilted and untilted versions of it. So this is the conventional and optically treated daylighting system with shading example. Then you can also have louvers and blind systems. So you have fixed and operable louvers and blinds. You can have them on both sides, but having it inside is a much easier system, because if you have them outside, you need to have certain controls or loops to make them go change shapes and things. There are buildings which use outside louvers systems and things. So they are also there. So you can have fixed and operable louvers and blinds. You can have translucent blinds such that part of the daylight comes in. Then you can have light directing louvers which reflect and allow only a certain amount of light to come inside. Okay. Then you have prismatic panels. So they consist of an array of acrylic prisms. So prism, is used for diffusing the light basically. So you have acrylic prisms with one surface of each prism forming an plane surface known as the prism packing. And they are often inserted in double glaze unit to eliminate maintenance. So you have normally if they are used in the vertical plane of facade to redirect light from the outside sky to the upper half of the inside room, usually the ceiling. So similar to your light shells, they reflect this light, they diffuse the direction to the upper half of the room, such that it does not enter directly to the lower half and cause glare and other effects. Then they can also be used to direct sunlight into a room to prevent glare and also color dispersion. The correct profile and season tilting of panels is essential because prism breaks it into these seven rainbow colors. So you also want to have a color dispersion and a correction system after this prismatic panel thing, such that those colors do not get distorted or create sort of illusionary effects for the occupants. Okay. Then, when used in a fixed sun shading system, they can be used in glazed roofs where they are designed according to movement of sun, such that the panels are integrated into a double glaze unit. Then, in a movable sun shading system, they can be placed in front of or behind the double glazing unit. So, double glazing is basically your window only. So, double glazing is when you have two layers of glasses instead of like one layer. So single glaze is just one layer of glass, double glaze is two layers of glass, triple glaze is three layers of glass, and so on. So in a movable sun shading system, they can be placed in front of or behind the double glazing in a vertical or horizontal arrangement, and they act as the sun shading device. Then another system is this laser cut panel. So you have the panel is basically divided by laser cutting into an array of rectangular elements. On the glass itself, they have done this laser cutting. So the surface of each laser cut becomes like a small internal mirror that deflects light passing through the panel. And very high proportion of light is deflected through a larger angle of greater than 120 degrees. And the maintenance of view through this panel is also needs to be considered because you have made these panels and cut it. So this view is also distorted. Then flexible manufacturing methods suitable for small or large quantities can be adopted based on the needs of your project or of your building. But this is also an option for daylight management. Then you have light guiding shades. So these are basically shades which consist of diffusing the glass aperture, and then you have two reflectors which are designed to either direct the diffuse light from the aperture into the building at angles within a specified angular range. So when you see the sun outside is much higher, you don't get it does not allow the direct component to enter this shell basically. But when the sun angle is low and when you have diffuse radiation, so then this allows the light to go in, which is why this you can see much more brightness compared to this previous picture. Okay. Then you have sun directing glass, which is a double glaze sealed unit or a double glass window that holds acrylic elements which cause vertical deflection or horizontal deflection. So these type of techniques can be used. I'm sure you have seen these type of structures, which are like light pipes or light tubes, basically. So these are tubular daylighting device. So they have this dome of light tube, and they're usually installed on roofs or the ceilings of buildings. So they capture this light. They allow that light to move into the light tube, and then they open it into the inside spaces basically. So this is the inside space. So these are different type of connections. So you can control the brightness. You can have a sort of lamp also to have it when during night time, especially if you're not storing this heat energy or the light energy. Then you have things like light tubes, which work on similar principles. Again, bringing the light inside, storing it. Then certain type of design considerations need to be made when you are designing buildings. So especially for skylights, there should be skylight spacing should be uniform such that light is uniform. Then splayed openings can be used to increase the apparent size of the skylights. Then you can place these skylights near the walls. You can use interior reflectors to diffuse the sunlight into larger opening areas, into like larger spaces. Then you can also use daylight control types. Daylight controls basically, so there are basically two types, which is the open loop and the closed loop system. So open loop system is used for measuring only the natural light, and it does not consider the electric lighting contributions. Whereas closed tube systems measure both the natural lighting and the artificial lighting, or your electric lighting contributions. Uh, and these can again be like switched daylight system, where you have the switching on and opening times, and you can have dim daylighting system where you can say that it should be operating at 100% intensity, or it should be operating at 50% intensity or 10% intensity during these time periods. So you can say all of these details like the dead band, delay time, fade time. So these type of descriptions you can give to your design systems, and they will ensure that your lighting is done in that order only. Okay, so this is all which was discussed in this week's content. This was just a quick brush up of whatever was discussed. So now we will look up at question and answers from week 4 assignment based from the previous one of this NPTEL course on principles and applications of building science. So the first question is, an articulation index of 0.2 would indicate A, speech privacy, B, speech clarity, C, good audibility, and D, none of the above. Okay, so the correct answer is speech privacy, or A. So we looked up at the articulation index as the ratio between the speech to the background noise basically. So if it is of 0.2 or less, it is a normal speech privacy, and above 0.4 there is no privacy at all. So these type of ratios are considered. So again, if it's greater than 0.65, it is good for communication. If it's greater than 0.4, there's no privacy. You can't hold a confidential talk. If it's 0.3 or less, then there's freedom from distraction. 0.2, you can have a normal speech privacy where two people can communicate in confidential manner. And if it's like not in confidential manner, but like have a one-on-one conversation easily and be understood. For confidential speech privacy, you have to maintain an articulation index of 0.05 or less, such that the person around you cannot listen to whatever you are talking. Okay, so like you are aware of the neighbor's conversations, but it is not intelligible. But in 0.2 articulation index, you have occasional intelligibility, or you can understand the topic on which they are talking, or a few words you can pick up. So also from a neighbor's conversation or work patterns are not interrupted. So an articulation index of 0.2 indicates a speech privacy condition. Okay, so A is the correct answer. So moving on to question 3, the clarity of sound is expressed as a ratio of A, signal to noise, B, given sound signal and a standard sound signal, C, sound energy arriving before and after the time threshold, or D, none of the above. Okay, so we also looked up at this in our revisions previously. So the correct answer is C, sound energy arriving before and after a time threshold. So a clarity index of C80, you can have C50, C80. So a clarification index of C80 measures the total sound energy arriving before an 80 millisecond threshold compared to the total sound energy arriving after the threshold. And this is averaged for 4 mid-frequency octave bands between 500 to 4000 hertz. So this is C80, which is you can also have C50, which measures the total sound energy arriving before the 50 millisecond threshold compared to the total sound energy arriving after the 50 millisecond threshold. So clarity of sound is before sound energy arriving before and after a time threshold. It can be C80, like 80 millisecond threshold, or C50, like 50 millisecond threshold. So C is the correct answer for clarity of sound. So again, the definition of the terms are important, as well as the units on how to measure them, and if there are formulas on what parameters and what type of quantity is affected. So in this, moving on to question 5. So a concave wall surface in a room might lead to A, focusing, B, creep, C, flatter echo, or D, none of the above. Again, this is looking up at the sound effects which can occur during the design of surfaces. So particularly a concave wall is responsible for focusing and creeping, where a lot of different rays gets focused on a particular point, and creep where the rays keep getting uh, deflected and do not reach audiences. So A and B are both possible through a concave wall. Okay, so moving on to question 6. The impedance tube method is used to determine A, sound insulation, B, vibration isolation, C, sound absorption, and D, sound diffraction. Okay, so we discussed this particularly relating to the calculation of the reverberation time. So we have the two different types of methods for determining the sound absorption of materials. So these are the reverberant chamber method and the impedance tube method. Further details can be found in the particular lectures on this topic. So the correct answer is C, that is sound absorption. So again, methods on how what methods are used for determining what are also essential from an examination point of view. So you can keep a lookout on those as well. So moving on to question 7. So performance of Helmholtz resonators depend on A, absorption in the cavity, B, cross-section area of neck, C, velocity of sound, and D, volume of the room. So these are based on the type of acoustic materials and a particular type, which is the Helmholtz resonators or the cavity resonators. Okay, so we looked up at this equation as well. So cavity resonators or Helmholtz resonators, their performance depends on the velocity of sound. So C, the cross section area of the neck. So if you remember the neck or the void through which sound can enter in the, so that cross section area of neck. So B is also correct. And then D, the volume of the room or the volume of the cavity V. So B, C, and D are all correct answers to this particular question. So moving on to question 9. Design sky luminance varies by virtue of A, latitude of the location, B, orientation of building, C, size of fenestration, or D, type of building. Okay, so we looked up at this also. So this was in the definition of design sky luminance. So the correct answer is A, the latitude of the location. So the design sky luminance is basically the location receives this illuminance 85% of the time between 9 a.m. and 5 p.m., assuming like on a horizontal surface. So the location basically determines the design sky luminance value. So the latitude of location, the longitude of location are both answers which could be correct here. So A, the latitude of location is the correct answer here. So moving on to question 10, open loop daylight controls measure A, only artificial light, B, only natural light, C, both natural and artificial light, and D, none of the above. Okay, so the correct answers here is B, only natural light. So open loop daylight control, they measure only the natural light and they do not consider the electrical or artificial lighting contributions. Whereas your closed loop type day controls, they measure both the natural as well as the electrical lighting contributions. So open is associated with natural light only and does not consider artificial light. So B is the correct answer. So moving on to week 3 assignment. So because the deadline for this for the submission of week 3 assignment has passed. So you can also look up at the solutions which are available. So we will now discuss the week 3 assignment for this run of the course. So the first question is, in a solar chart, the concentric circles represent A, altitude angle, B, azimuth angle, C, day of a year, or D, time of a day. Okay, so we have looked up in week 3 and also in week 2 the solar chart, the stereographic projection of the solar chart, which is basically the 3D movement of the sun on a particular location, represented in a 2D form. So it's like in a circular stereographic projection. So the concentric circles here basically are these. So this is basically the movement of the sun in a particular location. So these concentric circles are basically the altitude angle which the sun forms with the building. So the altitude angle goes from 90 in the center to 0 or 100, 0 or 10 and so on. It decreases basically from 90 to 0. So the concentric circles are basically the altitude angles. Then you have the azimuth angle, which is located on the circumference of the outermost circle. This is the azimuth angle which the sun position makes with the horizon. Then you have the date lines, which are basically these lines on which the sun moves on the particular different months. So you have some January, February, March, April, May, June, and then there are here some July, August, September, October, November, December. So goes from January to June here and July to December here. And then these are the hour lines. So they basically correspond to different hours of the day. So this is 6 a.m. So sun rises much in December, sun rises close to 5. Uh, close to 5. And then it sets at 7, close to 7. So 19 is 7, 18 is 6. So this is the hour lines basically. So if you want to calculate where the sun is at a particular day or the particular time, so you can just select the day, select the hour. If you know the altitude and azimuth angle, you can also calculate where the sun is. So by just connecting if you know the azimuth angle is 45 and if you know the altitude is 30. So when you join this to the center, azimuth line to center, wherever the 30 altitude angle intersects, that is the position of the sun for that particular altitude and azimuth. So this is how you determine the position of sun in this stereographic projection or the sun chart or the solar chart. So to answer this question, the concentric circles are basically the altitude angle. So A is the correct answer. So moving on to question 2, the unit of loudness is A, phones, B, decibels, C, watts, or D, zones. Okay, this was again discussed in week 3, acoustics basics. So the correct answer is A, phones. So loudness is this property of sound which determines the intensity of the sound that is being produced. So the loudness of sound as perceived by an average human is directly proportional to the logarithmic value of the sound intensity. And the SI unit of sound is phone. So one phone is defined as the number of decibels of a sound whose frequency is 1000 hertz. So the correct answer here is A, phones. So moving on to question 3, compared to a female voice, typical male voice has a slightly higher predominance of A, high frequency, B, low frequency, C, mid frequency, and D, none of the above. Okay, so the correct answer here is low frequency. So this is asking, this question is particularly asking about the typical male voice in comparison to the female voice. So the typical male voice has a lower frequency compared to the higher frequency of female voice. So the correct answer is low frequency. So B is the correct answer here. So moving on to question 4, sound pressure is measured in A, watts, B, decibels, C, pascals, or D, hertz. So again, units are important for different properties and they can be asked in the questions for your particular examinations as well. Okay, so the correct answer here is Newton per meter square or pascals. So sound pressure is measured in newtons per meter square, whereas sound pressure level is measured in decibels. So all of these sound levels, sound intensity levels, or sound pressure levels, sound power levels, all of these levels are measured in decibels, whereas all of these different units have different values. So the reference uh, pressure value is 20 micropascals, which is 2 into 10 to the power minus 5 Newton per meter square, or 2 into 10 to the power minus 5 pascals. So C is the correct answer. That is sound pressure unit is Pascal. Okay, so moving on to question 5. Two similar sound sources with sound pressure level of 80 decibels each, when operated together, will result in a total sound pressure level of A, 60 decibels, B, 120 decibels, C, 80 decibels, D, 83 decibels. So again, we discussed this in the acoustics basics. So if two similar sound sources are present, they will together have an increment of 3 decibels. So if the sound pressure level of the first source is 80 decibels and the second source is also 80 decibels, so together their sound pressure level is going to be 80 plus 3 decibels. So this is 83 decibels. So option D is the correct answer. You can also achieve the same by calculating using the formulas as well. But this is a direct hint or a direct observation from the uh, same things. But you can derive the same thing also from the formulas for the sound pressure level. Okay, so moving on to question 6. In unobstructed outdoor environments, the sound pressure level of a non-directional source reduces by dash with double of distance. So the option is A, 3 decibels, B, 10 decibels, C, 6 decibels, and D, 12 decibels. So by how much decibels does the sound pressure level decrease if we double the distance from the source? Okay, so for this, we can solve the equation. So we have the sound pressure level of uh, the first case where we are at a distance of R1. And then we have the another case where we are at a distance of R2. So R2 is basically twice of R1. So if we solve this formula for 20 log R2 by R1, we get 20 log 2. So R2 is basically 2R1. So we get log 2, which is 0.301. So we get 6 decibels. So by the sound pressure level of a non-directional source reduces by 6 decibels if we double the distance between the source. Okay, so C is the correct answer. So again, these formulas are important, and I'm sure you would have solved these questions as well. So moving on to question 7, the equivalent sound pressure level, LEQ, is also known as A, time integrated sound pressure level, B, pressure integrated pressure level, C, weighted sound pressure level, or D, integrated sound pressure level. Okay, so the correct answer here is A, that is it's the time integrated sound pressure level. So LEQ, as you can also see from its equation, it integrates the sound pressure level over time. So the correct answer is A, the equivalent sound pressure level LEQ is also known as the time integrated sound pressure level. So A is the correct answer here. So moving on to question 8. So when the directionality factor is 8, the perceived sound pressure level increases by A, 9 decibels, B, 6 decibels, C, 3 decibels, and D, 0 decibels. So we looked up at the directionality factors when we looked up at directional sound sources. So the directionality factor is the ratio of intensity on a designated axis of a sound radiator at a stated distance to the intensity that would be produced at the same position by a point source if it were radiating the same total acoustic power as the radiator. So directivity index is given by the equation of 10 log 10 Q naught. So our Q naught is basically 8 here. So Q naught 8 here, so log 8 to the base of 10 is close to 0.9. So 10 into 0.9 is 9 decibels. So the correct answer here is A, 9 decibels. So again, these formulas are important, as well as understanding how the formula is being derived, what is the definition, what is the unit, the different parameters is also important again. So A, 9 decibels is the correct answer. So if it was 4, if the directivity factor was 4, then it would have increased by 6 decibels. If the directivity factor was 2, then the sound pressure level would have increased by 3 decibels. If it was 1, it would have been 0, because log 1 is 0 basically. So it would have been 0. It would have increased by 0 decibels. Okay. So moving on to question 9. Two sound sources with sound pressure level of 60 decibel and 120 decibel when operated together will result in a total sound pressure level of A, 110 decibels, B, 120 decibels, C, 113 decibels, and D, 116 decibels. Okay, so again, you can achieve the same thing by solving as well, but because if the if one sound source is much significantly or sufficiently quieter than the other sound source, then the total sound level remains at the higher sound source level. So because these sound pressure levels are actually translated on the log level, the actual value of the pressure is much lower, because it's the pressure level is in the power of 10 to the power minus something. So if you translate 60 decibel, it's going to be a much quieter pressure value compared to the 120 decibel actual pressure, sound pressure value. So when both of these sound sources are acting together, you'll get a total sound pressure equivalent to 120 decibels. So you can achieve the same thing by solving the equations as well. But if you want to quickly solve the questions, you can just remember, if the sound source is one of the sound sources much higher in the decibel scale then the other sound source, then the higher sound source is the total sound pressure level which will be achieved. Okay, so in this case, the higher sound source is 120 decibels. So the correct answer is B, 120 decibels. Okay. So this is again directly from the basics which I had picked up, but you can achieve the same things by solving the sound pressure level equation for the two different sources. Okay, so moving on to question 10. So a seminar hall has a volume of 2000 cubic meter and the total absorption of all acoustic materials without any audience is 80 meters square Sabians. The reverberation time of the empty hall in seconds will be A, 1 second, B, 2 seconds, C, 3 seconds, and D, 4 seconds. Okay, so we have looked up at the reverberation time equation, or the Sabin equation. So which is so we are given the volume of the seminar hall, which is 200 cubic meter. Then we are given the total absorption of all acoustic materials without any audience, which is given as 80 meters square Sabians. So our absorption and our surface area total has been given as 80 meters square Sabians. So our reverberation time is calculated as 0.163 volume by this A value. So when solving this equation, we get 4.075 seconds. So D, 4 seconds is the correct answer. So again, equations and numericals can be expected in the examination. So please focus on the equations and know what are the different parameters, what are the constant values. Okay. So with this, we come to the end of our session. Okay. So since we do not receive any queries relating to week 4 content in the discussion forum, we will not we do not have anything to discuss in this section. So thank you so much for attending this session. And if you had any feedback regarding the problem solving sessions, regarding the course itself, you can give the feedback in the feedback forms which are being circulated to you through emails. You can give the feedback on the problem solving sessions also. There will be a survey which will be done after the problem solving sessions are over. So please give your feedback on what could be improved for the next one and things like that. And thank you so much for joining. And I wish you all the best for your exams. If you have any questions, you can still post them in the discussion forums. We will keep replying to the questions received in the discussion forums until the examination date. So, wish you all the best for the final examination. And I hope these sessions have been helpful to you. So, I think I will close the session now.